Hello and welcome back to Math 152. We're going to continue along Chapter 4 today, and in particular Section 4.4, we're going to cover some counting techniques. As you have seen, in doing the sample space for probabilities, counting is the necessary thing that we have to go through. So this section covers different ways that we can do counting without actually having to list out all the different elements. So this time we're going to count the number of ways a sequence of operations can be performed, count the number of permutations, and then count the number of combinations, and we'll cover what those mean. So objective 1 is to count the number of ways a sequence of operations can be performed. So this is the fundamental principle of counting that we're going to use in different ways. But if an operation can be performed in m ways, and a second operation can be performed in n ways, the total number of ways to perform the sequence of two operations is just m times n. So in general, if a sequence of several operations is to be performed, the number of ways to perform the sequence is found by multiplying together the number of ways to perform each of the operations. So here we have an example. A certain make of automobile is available in any of three colors: red, blue, or green, and comes with either a large or small engine. And how many ways can a buyer choose a car? So how many ways do we need to, how many different car types do we need to have out on the grounds in order to have a representative of each one of these cars available for the customer? So if we have each one of these, so if we pick out a red, it's possible to have either a large or small engine. We could have a blue large or small engine, and then a green large or small. So we had 3 times 2 would be 6. 1, 2, 3, 4, 5, 6. So that's how basically the counting principle comes apart. We just count the number of one operation, the color, and then the second operation is to choose a size of the engine, so 3 times 2. Here's another one. License plates in a certain state contain 3 letters followed by 3 digits. How many different license plates can we make? So there are 6 operations in all, choosing 3 letters and choosing 3 digits. There are 26 ways to choose each letter, and then 10 ways to choose each digit. So the total number of license plates is therefore, this is the first one, we choose 26. The second is the second letter, 26. Third letter, 26. And then here are the numbers, times 10, first number, times 10, the second number, and times 10, the third number. So we would have 17,576,000 different combinations of license plates that we could come up with. So another thing that we're going to have to be able to calculate is the number of permutations. So the word permutation is another word for ordering. So when we count the number of permutations, we are counting the number of different ways that a group of items can be ordered. So here before we were just saying if we could do it like, remember the license plate with numbers, it was 10 times 10 times 10 for the numbers. But if I can only use one of those numbers once, I would have to have one of the 10, and then once I've used that, I'd have to reduce it by 1. I'd only have 9 remaining, then 8 remaining, 7 remaining, all the way down to just the 1 remaining. So the number of permutations of n objects is n factorial, and n factorial is just start with n, subtract 1, multiply that number, subtract 2, multiply that number, and keep counting all the way down to 1 and multiply those numbers together. That's the n factorial. So we have 5 runners running a race. One of them will finish first, another will finish second, and so on. And how many different orders can they finish? Now, remember that the order makes a difference in this case, so we want to know who the first one is, second, third, fourth, fifth, but how many ways can we get those 5 runners to go? So the number of different orders the runners can finish is 5 factorial work. We want all those 5. So we're basically doing the same counting principle again, But in this case, the first position, I've got 5 people who 5 of the runners can do first. And once that first position, we have 4 of the remaining runners for second, 3 for the third, 2 fourth, and 1 for the fifth position. So there's 120 different ways that these 5 runners can finish the races. If 10 runners run a race, the first place finisher will win a gold medal, the second place finisher will win a silver medal, and the third place finisher will win a bronze medal. And how many different ways can the medals be awarded? So here we've got 3 different categories that we're working with, first, second, and third. The first, any one of the 10 runners can come up with the first position, so we've got 10 golds. But once that first is chosen, we have got only 9 that can fill in the second place. And then once that one is fixed, we go to 8. So 10 times 9 times 8 is what we would look for. So we use the fundamental principle of counting, 10 possible choices for the gold medal. Once the gold medal winner is determined, there are 9 remaining choices for the silver, and then 8 remaining choices for the bronze. So this is the easiest way to do this when things are ordering, is just counting out. You can't repeat things, and you just go on 10, 9, 8. So it would be 720 ways. So another way of saying that is this is the permutation of R objects chosen from N. The permutation of R objects chosen from N. So in that last examples, we had 3 runners were chosen from a group of 10, then ordered as first, second, and third. This is referred to as a permutation of 3 items chosen from 10. In general, a permutation of R items chosen from N items is an ordering of the R items. It is obtained by choosing R items from a group of N, then choosing an order for the R items. So this can be found by basically N PR, permutation of R items on N, is N minus 1, all the way through the N minus R plus 1. We just saw that 10, 9, 8 till we stop. But another way to do this and represent it in mathematical terms is go N factorial and then divided by N minus R factorial. So this basically canceled out all the rest of those in a mathematical terms. So 5 lifeguards are available for duty one Saturday afternoon. There are 3 lifeguard stations, and how many ways can 3 lifeguards be chosen and ordered among the stations? So we need to be able to choose 3 out of those 5 and order them. So the 5 factorial divided by 5 minus 3 factorial, that's the 2 factorial. And here, if I expand this, 5, 4, 3, 2, 1, you see that 2 times 1 is the 2 factorial. This is the 2 factorial. So all of those will be canceled out. And we just have 5 times 4 times 3 left up here to calculate, and that gives us the 60. So here we're going to count combinations. Combinations are very similar, except we're not interested in the order. So ordering is not important, and the most common example would be a hand of cards. Once I've dealt that hand of cards, I'm free to shuffle them around, but it's the very same hand of cards. So in some cases, when choosing a set of objects from a larger set, we don't care about the ordering of the chosen objects. We care only which objects are chosen. For example, we may not care which lifeguard occupies which station. We might care only which 3 lifeguards are chosen. Each distinct group of objects that can be selected without regard to order is called a combination. So the number of combination of R objects chosen from N is, this is the C, this is the N, choose R. How many ways can I choose R objects from N? Is the N factorial, looks just like the permutations, N factorial to N minus R factorial. But then I'm going to also divide by r factorial. This gets rid of all of the combinations that would have been from a permutation. So if you had first, second, third, it wouldn't matter if it was 2, 1, and 3, 3, 1, 2. That gets rid of that possibility. So at a certain event, 30 people attend. 5 will be chosen at random to receive prizes. The prizes are all the same, so the order in which the people are chosen does not matter. How many different groups of 5 people can be chosen? So this is how many different prize lists can we come up with? Since the order of the 5 chosen people does not matter, we need to compute the number of combinations of 5 chosen from 30. So 30 choose 5, 30 factorial, the 35 minus the 5 factorial, and then also that 5 factorial still in the division. So once we do this, the 25, that's 25 factorial, all the 25 factorial divides out, and I'm just left with the 30, 29, 28, 27, 26 divided by this 5 factorial. And that gives us 142,506. These are the 5 people from those 30, and it doesn't matter, all of, Jim, John, Jack, Tom, and Nancy, it doesn't matter which order those are the same set of prize winners. So here's how we can do this on the TI-84, and the 36 and the 30 have their own little peculiar ways to do it. We can cover those in lab. So if I want to do it on the TI-84, I enter the math menu, and then I go over here to the probability. I do my right arrow, and then I go down here, and I've got the 3 operations that we've talked about. The number of permutations are permutations on n, the number of r combinations of n, and then the factorial operator is this. So we just go down, you would enter the first number. So if I wanted to do 10 permutations 3, 10p3, I'll do 10, go inside the math, hit this, and then do the 3 once I've gone down. And this was what it would look like for running a couple of these things. If I wanted to do 5, number of 3 permutations from 5, I would do 5, select that NPR through the math probabilities menu, add the 3, and then do enter, and it would give me the 60. 5 choose 3 would be 10. So here is a good example of using these counting principles, and we want to use them in probability, and that's the kind of the key of what we're doing. We're doing probability now, but as we go forward, we're going to be merging probability and statistics. So we're going to use the 2 of them together. So here I've got a box of light bulbs containing 8 good light bulbs, 2 burned out bulbs. 4 bulbs will be selected at random to put into a new lamp. What is the probability that all 4 bulbs are good? Okay. So I've got 8, 9, 10 light bulbs that I'm going to choose, and I need to get 4 of them. So I'm just going to mix them all in. Don't know which one is which. Go in there and grab 4 at random. How many combinations could I've got just out of the 4? So if I went through and listed them and removed all the ones that were just different ordering of the same set of light bulbs, I would have 10 choose 4. So out of the total 10, I'm going to choose 4. There's 210 unique combinations where order doesn't matter. But now I was only concerned about, I want all those 4 light bulbs to be good. So now I need to do, well, what's that probability that 4 good bulbs are selected? Here was the 210. That was just any 4. Now I want all 4 of them. Well, how do I get this? I want to do 4 out of the 8. How many ways can I get 4 bulbs out of these 8 good ones? And that's the 8 choose 4. 8 factorial, 4 factorial, 8 minus 4 factorial. That'll give me 70 different ways that all 4 of them are good out of those 4 different ones. Okay. So that gives me the 70 divided by 210 is the 1/3. So there's some of the fundamental examples, and we'll do others in the lab time. But you should understand the fundamental principle of counting. I have something that goes m ways, and the next process is n ways. It's m times n. How to count the number of permutations of n objects. That's NPR, and that is with ordering. So ordering is important: first, second, third. If I need out of a team of 20 people, I need 3 officers. So that would be like president, vice president, treasurer. I would use the 20P3 because those orders are different. The president, the vice president, and treasurer are important. If I just want to do the combinations, I don't really care. I just needed to pick 3 people out of the 20 to do a task, and the order doesn't matter. Those are just 3 of those, how many ways I could get that combination of people. So we did the permutations and combinations using the TI-84 plus, and then we basically used probabilities that we did 2 sets. If we had distinct groups, we would want to know just how many overall ways to give us our sample set count, and then the particular ones to get whichever one we're looking at. Okay. So that basically finishes it up for chapter 4, 4.4, and hope you found it instructive. See you next time.